So I'm now going to talk about a systematic way of deriving high-order Runge-Kutta methods, and this goes by the idea of what is called collocation. So at first blush, these methods may not appear to be Runge-Kutta methods, but we'll show that they derive or they induce a natural class of Runge-Kutta methods. Okay, so let's start with the setup. Let's say that you have a bunch of collocation points, which are normalized to be in the interval from 0 to 1. And without loss of generality, I'm going to order them because I'm going to assume that they're distinct. Okay, so C1 to CS, and these are distinct points. Okay, so associated to this, we're going to consider what is called a collocation polynomial. Which I denote by U of t. Okay, so U of t is going to be something which you should think of as being a discretization of the conditions for something being the solution of a initial value problem. So you know U at t0 is some initial condition y0. And then what's going to happen is that if you had an honest to goodness initial value problem, then what is going to happen is that for every time that curve U of t is going to satisfy a differential equation. Okay, but because we're going to look for a polynomial which only has a finite number of degrees of freedom, we're not going to be able to require that the curve satisfies the differential equation at every point in time. But you can require that it satisfies the differential equation at the collocation points. Okay, so that's what's going to happen. So when you take u and you differentiate it and you evaluate it at time t0 plus CIH, then this is going to satisfy the differential equation. So this is going to be f of u at t0 plus CIH. Okay, and this is going to be true for I equals to 1 to S. So now with these two things, you have S plus 1 conditions. Okay, so you could imagine that this uniquely specifies a polynomial of degree up to S. Okay, so so you want that U of t is a polynomial of degree S on the interval and it's a polynomial in t. Okay, and then the idea then is that the numerical method you get is by evaluating this polynomial, this collocation polynomial U of t at the appropriate time. So the numerical method, right, is obtained by evaluating U of t at basically t0 plus h. Okay, so that's saying that y1 is equal to u of t0 plus h. Okay, so again, it's like you can imagine this is a way of imposing the differential equation, but again only at a discrete set of points. Okay, and you choose, it's like the number of points so that you have a unique polynomial which satisfies this. Okay, so you might ask, how do you actually go about writing this down, and how is this related to a Runge-Kutta method? Okay, So let me just keep on going. So let's say that you have these fi's, which are the values of the interpolating polynomial at the nodes, and you don't happen to know what they are yet. Okay, so let fi be the value of the derivatives of ut at the nodes. Okay, so what I mean by that is that fi is defined to be u prime at t0 plus CIH. Okay, and again, this is for I equals 1 to s. All right, so let's go from there and see what happens. So the basic idea then is that if you have u of t, which is a polynomial of degree s in the variable t, then of course its derivative, u prime of t, is a polynomial of at most degree s minus 1 in t. Okay, and so you know that if you have a polynomial of degree s minus 1, then it is uniquely determined if you happen to know what its value is at s distinct points. Okay, so u prime of t can be exactly and sort of reconstructed given sort of s distinct sample points. Okay. And as before, it's like I said that these fi's are just u prime at t0 plus CIH, okay, where the CI's are the collocation points. Okay, so what this is telling you is that u prime can be expressed in terms of its corresponding Lagrange interpolating polynomial in s points. Okay, and that expression is going to actually recover for you u prime. Okay, so I can write this as this linear combination I equals 1 to s of fi, then the Lagrange polynomial li. Okay, and again, usually the Lagrange polynomials are defined, it's like on the interval from 0 to 1. So when I write this actually in terms of t, which is defined from t0 to t0 plus h, I have to do a rescaling. So I write this as t minus t0 over h. Okay. So what you want to do now, okay, is to remember that you know what u at t prime is. So you know at u at t0, okay, that's just y0. So of course what you can do is you can then use again the fundamental theorem of calculus to evaluate what u is. Okay, so now u at t0 plus CIH, okay, is u at t0 plus the integral from t0 to t0 plus h of u prime of tau d tau. Okay. Okay, so so that's basically what you have so far, and so now actually I'm sorry, I have to integrate this from t0 to t0 plus CIH. Okay. And again, I replace u prime. It's like using the Lagrange interpolating polynomial. So this is u of t0 plus the integral from t0 to t0 plus CIH, sum from I equals 1 of fi, the Lagrange polynomial, okay, t minus t0 over h d t. Okay, and what you can do then is that you can do a change of variables. So this gives me u plus t0 plus, okay, and I change the order of the sum and the integral. Sum from I equals 1 to s. Okay, there's a factor here. It's like from the Jacobian of the transformation between the interval, and then the limits of integration that get transformed from t0 to t0 plus CIH to 0 plus to CI. And then there's an fi here, and then there's the Lagrange polynomial Li of x dx. Okay. Yes, I'm sorry. So this index is I. I have to change the sum here to an index over j. Okay, and I'm going to do this here. J. All right. So now it's like you're in business, right? Because this is again the value of the vector field that's like at these collocation points. Okay, so I'm going to think of these as the coefficients of a Runge-Kutta method. So this is going to be aij. Okay, so let's try to write this. You're going to have aij is going to be the integral from 0 to ci of the Lagrange, the jth Lagrange polynomial, and then the bi's are the integral from 0 to 1 of the ith Lagrange polynomial. Okay, and this is again consistent with the idea that the bi's correspond to the quadrature weights where you've taken a full step of length h in order to get the approximation of the solution at the new time. Okay, so let's just keep this here for now and see what happens. Okay, so then this collocation condition can be written as following: that fi is equal to f at y0 plus h sum from j equals 1 to s of aij f at j. Okay. All right. And again, as you might imagine, it's like when you integrate the defining equation. Okay. So if you have again u prime of t is equal the sum of fi Li t minus t0 over h, I equals 1 to s, right? When you integrate this over the interval from 0 to 1 and apply the initial condition, then this implies that y1 is equal to u at t0 plus h, okay? And this is equal to y0 plus h times the sum from I equals 1 to s of fi, and then the integral from 0 to 1 of Li of x dx. and again, these are the BIs. Okay, so this is telling you that y1 is equal to y0 plus h sum of bi fi, which is, of course, the usual form of a Runge-Kutta method. Okay, so in any case, it's like what this is basically telling you is that if you look at these methods of collocation type in practice, they reduce to a very specific type of Runge-Kutta algorithm, where the aij's and the bi's are given in the following way once you specify the collocation points C1 to CS. Okay, so let me sort of just summarize all of that. So the point is that the resulting method is of Runge-Kutta type. Okay, where if you are given the collocation points, C1 to CS, and again, as a reminder, they have to be distinct. Okay, then we have the corresponding Runge-Kutta coefficients. Okay, which are given by aij is the integral from 0 to ci of ljx dx. Okay, and as a reminder, it's like the lj's are the Lagrange polynomials, and they are defined to be the product of the following expressions, right? So that x minus ci, cj minus ci, and they have the Kronecker delta property, right? That li evaluated as cj is equal to lj evaluated as ci, if you prefer, is equal to 1 if I is equal to j, and 0 if I is not equal to j. Okay. So let me just make a few remarks about these sort of collocation Runge-Kutta methods. So the first one is that not all Runge-Kutta methods are of collocation type. And it's easy to see this because if you recall, when we looked at this fourth-order explicit Runge-Kutta method, it had a C vector which was 0, 1 half, 1 half, 1. So the CI's were repeated, if you will, and that's not possible when you're looking at least these standard collocation methods. Okay, so not all Runge-Kutta methods are collocation methods because there are RK methods with non-distinct CIs, right? So that's the first thing. And the second remark is that once you've specified the CIs, once you specify the collocation points, then there's of course a unique Runge-Kutta method associated with it. So given distinct collocation points, there is a unique RK, well, collocation RK method associated with this. Okay, So another way to then check whether or not a method is a collocation Runge-Kutta method is to just look at this vector as C's, substitute it into the expression for the Runge-Kutta coefficients. I'm sorry, I forgot to also add the expression for the BIs, right? So BI is the integral from 0 to 1 of Li of x dx. Okay, so together it's like these things specify a Runge-Kutta method. Yeah, but again, the point basically is that if you specify the C1s to CSs, then there's a unique, it's like A matrix and B vector associated with this. And so one very, very easy way to check whether a Runge-Kutta method is a collocation method is to first see whether or not the C1s to CS are distinct. If they're not distinct, then you're done. It's not a collocation Runge-Kutta method. If they are distinct, then the next thing you should do is that you evaluate these AIJs and BIs from this formula, and then you compare it's like the resulting Runge-Kutta coefficients to the one which you have, and if they're different, again, that's not a collocation Runge-Kutta method. Okay, and the third remark is that if we recall, even though it's not readily apparent from, it's like the Runge-Kutta form of this, at the back of these collocation methods is this collocation polynomial u of t, which satisfies the differential equation at distinct points and which has the same initial condition. So what then this implies is that collocation methods then give you a continuous approximation of the solution u of t as well. So so the continuous approximation is given by this u of t, which is the collocation polynomial. And of course, in general, with a Runge-Kutta method, you don't necessarily have a continuous expression which can be viewed as an approximation of the solution of the differential equation. All right, so let me just stop here for now.